Hey, fellow mathers. Before we get into this episode, we want to share with you how you can get access to free content, professional learning that will keep your students engaged and doing the math that matters. Get ready to go to this link, mathisfigureoutable.com/challenge.
That's right. Registration is open for the free Math is Figureoutable Challenge that's starting May 15th and runs to the 17th at 7 p.m. Central. We're going to have 3 nights jam-packed with learning and routines that you can take straight to your classroom.
In these challenges, we have a great time. We do some math, talk about classroom experiences, give away super cool bonuses and prizes. You won't just walk away with routines that are naturally engaging and encourage your students to think mathematically. You'll also have a chance to win over $6,000 worth in prizes, including a few virtual PD sessions for your school. I'll be joined by my wonderful co-host Kim and special guest Jenna Labe.
You can register at mathisfigureoutable.com/challenge for a fantastic learning experience. That's mathisfigureoutable.com/challenge. Now on to the show.
Hey, fellow mathematicians. Welcome to the podcast where math is figureoutable. I'm Pam.
And I'm Kim.
And we make the case that mathematizing is not about mimicking steps or memorizing facts, but it's about thinking and reasoning, about creating and using mental relationships. We take the strong stance that not only are algorithms not particularly helpful in teaching, but that mimicking algorithms actually keeps students from being the mathematicians they can be. We answer the question, if not algorithms and step-by-step procedures, then what?
All right, y'all, we are in part 4 of our series where we answer the question, if not algorithms, then what? We've already tackled addition and subtraction, and today we're going to tackle multiplication. What are the major strategies that we think students and anyone really need to know?
Because if they own these 5 major multiplication strategies, then we can throw any multiplication problem that's reasonable to solve at a calculator, and they will be fine. They will be able to solve it as efficiently as a traditional algorithm, and most of the time more efficiently than the traditional algorithm. But even more important than that, they'll be developing multiplicative reasoning. That is our goal. We want to develop reasoners, not just answer getters.
Okay, so the 5 major multiplication strategies are smart partial products, over under, 5 is half of 10, double half, and quarters.
All right, you got him. Okay, thank you for joining us on the... I know we made that joke last time, but I'm going to keep making it a little bit because we really want to emphasize it's not about the names and it's not about us telling you these strategies. Now that we've sort of laid them out, now you need experience, your students need experience to develop these relationships, actually create the relationships in your heads that these strategies are based on so that the strategies become natural outcomes. They become natural inclinations. As you look at numbers, you're like, oh yeah, like this pings for me. And so now I'm going to use this strategy. And that's all about developing that reasoning, that level of reasoning that we're really after, not just answer getting. All right.
Go for it.
One of us say all right again. All right. Okay. All right. Ready, begin.
Okay. This week, we're going to tackle these strategies with the problem 25 times 18.
All right.
Which I just wrote down with my pencil.
With my pen. Pen, Kim. Pen.
Okay. 25 times 18.
We should do a listener survey. How many of you write in pencil? How many write in pen? And then give all the people that do it correctly with pen. Just kidding. Send them a sticker. Maths is figureoutable.
There you go.
All international math. All right. 25 times 18.
Yep.
So similar to addition, a first strategy that we need to develop in students is kind of the place value splitting strategy. And we typically call that, with multiplication, we typically call that partial products. In addition, we called it partial sums. You may have noticed, if you listened to the last episode, that in subtraction, we didn't really talk about partial differences. We don't find partial differences to be all that helpful with students. It's okay if students do it. We support them, but we don't actively promote constructing it with students. However, with addition, partial sums is important. With multiplication, partial products is going to be important. So that is an important start, but it's just a start. that then we need to move and build the next 5. We need to build on that. So what is partial products? That's when I look at thinking about 20. Again, it's sort of a place value splitting thing. I look at 25 as 20 and 5, and I look at 18 as 10 and 8. And then I look at all of those partial products. A typical way that we might see teachers help students with this, and we like this is fine, is for students to think about an area model of a 25 by 18, and I'm drawing a rectangle right now that's about 25 by 18. You might have noticed that I said I'm drawing a rectangle because, to be clear, a 25 by 18 should be a rectangle, not a square. Now, a square is a rectangle, but it should be not a square rectangle. It should be a longer than wider rectangle. It should be 25 long, 25 deep, and 18 across. And that should be not look like a square. So if you're drawing a square, maybe we politely suggest that we're not developing a very good spatial reasoning if we make something that should be long and not as wide, if we make it look square. No, it should look like a 25 by 18. And then I would want to think about where I would sort of cut that 25 to make it 20 and 5. So I just sort of have a long part that's 20 and a much shorter part. Oh, it's about a fourth of that 20 to be a 5. And then on the 18, I'm going to cut that as a 10 and 8. So the 10 should be longer than the 8. And now I have kind of 4 chunks. And those 4 chunks, I would want to think about the 20 by 10 chunk, and that would be 200. And I would want to think about the 5 by 10 chunk, and that's 50. And I would want to think about the 20 by 8 chunk. I hope you're sort of drawing these out. And I would think about that 20 by 8 chunk, and that's 160. And then I want to think about that 5 by 8 chunk, and that's 40. Now I've got all these sort of partial products, all these little bits of area, and I would want to add those bits of area up. So if I add the 200 plus, oh golly, where do I go from here? Now it's actually kind of fun because now you can kind of decide how you're going to add those up together. But to maybe make it easy on a podcast since we're just listening, I might add that 200 and the 160 to get 360, and then add the 40 to get 400, and then add the leftover 50 to get 450. So sort of added those up, and I'm thinking that maybe the product is 450. What do you think? All right, cool.
Yeah.
That's like a baseline. That's a starting place. We're not ending there. But we're also not suggesting that the end is now, okay, now that you've kind of understood multiplication, now we're going to go do this algorithm that is so digit oriented and so like these columns, and then I end up with all these numbers and columns that I'm going to add. All that could be very sort of step-by-step rote memory. No. Now that's a baseline. Now we want to go and develop these other 5 strategies.
Yeah.
So Kim, I think the first one that we would develop from there is
smart partial products.
We're
taking kids from these place value partial products into smart partial products, which means that they don't have to break everything up into those same 4 place value chunks. So for 28 times 15,
18.
Sorry, 25 times 18.
Did you just totally flip both numbers?
I did.
That's hilarious.
Would not be the same thing. 25 times 18. I think if I was thinking smart partial products, I would think 25 times 10, which is 250. And then 25 times 8, which I know is 200.
Whoa, you did that kind of fast. Do that again. How'd you do
25 times 10
Uh-huh.
from the 18. So I split up the 18 into 10 and 8. So 25 times 10, which is 250. And 25 times 8, which is 200. Can
you talk me through how you knew 25 times 8?
Oh, because 25 is quarters. And so 25, 8 quarters would be $200, which is 200 cents.
So I could think about 4 quarters being 100. So 8 quarters would be 200. That'd be a way to do that.
Yep.
Can also think about the fact that you just had 10 quarters, using that times 10 thing to be 250.
Yep.
But I need 2 less quarters than that.
Mm-hmm.
So that's also 200.
Yep.
There's a couple different ways to do that. So I noticed, Kim, that when you did that smart partial products, or maybe we'd call it clever partial products, that you broke up the 18 the same way I did into 10 and 8, but you left the 25 whole.
Mm-hmm.
And because you could think about 10 25s and 8 25s. You were being smart about it. You're being clever about it. You're like maybe lazy about it.
Yeah.
Like let's only break it up as much as we have to, not into the same 4 chunks every time, but rather, like can I be smart about it? Nice.
Yeah.
Nice.
Yep.
That's smart partial products or clever partial products. Cool. All right. How about?
Oh, next you
Yes.
get to do one of my favorite strategies.
Oh, you're gonna let me, huh?
Yes.
Nice.
I will.
All right, let's do the over-under strategy. Over-under. So for 25 times 18, I want to think a little bit over and then go a little under. So I'm going to think about 25 times 20 because I can sort of think about 25 times 20. So I'm actually drawing another area model, and I'm drawing a 25 by 20. And I'm saying to myself, well, I know that area of that whole thing is 500. And I did that by thinking about 2 25s is 50, and then I scaled that up times 10 to be 500. I could have also thought about that as 10 25s is 250, but I need double that. Double 250 is 500. So a couple different ways to think about 20 25s, but I only need 18 25s. So instead of a 25 by 20, I'm going to do 25 by 18 by getting rid of 2 25s. So I have that 500 was the total, and I'm getting rid of 2 25s, which is 50, and 500 minus 50 gets me to that 450.
Nice.
So an okay over?
Very good.
Hey, Kim, I'm curious, since you're the over queen, would you ever think about doing, for 25 times 18, would you ever think about doing 30 18s and getting rid of 5 18s?
I mean, I could, but I don't think I would.
I can tell you why I wouldn't. I could think about 30. No, none of those are nice for me. 30 18s? I don't know 3 18s. I know 2 18s.
I do. And so I don't know why I do, but I do.
54?
Yeah.
It is. Yeah.
Good. Yeah.
I had to think about it though. But then also, once you had 30 18s, then I'd have to figure out 5 18s. And I can do that because I could do 10 18s to get 5 18s.
That's the part that's a little, that's yuckier for me.
That's more hanky for you.
The 90 I have to think about.
Yeah. So we could, but both of us are like, nah, but probably not.
Yeah.
And that's the kind of choice we want to give kids.
Right.
We want kids to be able to do exactly what we just did. I mean, I could, but nah, there's a better one. The other one, in fact, honestly, neither of the two we've done so far are my favorite for this problem for 25 times 18. Or any of the ones we've done. Partial products is not my favorite. I mean, I can. Smart partial products, I think you did a great one. I could. Just over and under, I mean, I could, but not my fave. Not for this problem. So what's the next strategy?
5 is out of 10.
All right. That's on you, I think.
I was hoping you would let me do the next one.
Oh, okay. Well, then I'll do 5 is out of 10. Okay, so I'm going to think about 25 times 18.
Okay. By
thinking about, I'm not going to break up the 18 this time. I'm going to break up the 25 into 20 and 5. So I'm going to think about 20 18s. And I'm actually asking myself if I'm going to do that on an area model or a ratio table. And I think I'm going to do it on a ratio table. So I'm thinking about 18s. And I'm going to think about 10 18s is 180. So 20 18s is 360. I could have thought about 2 18s is 36 and then scale that up to get the 20 18s is 360. Either ways, I have 20 18s. Yeah. But I did the 10 on purpose because I knew I was going to try to get the 5. Does that make sense? So I could have done 2 to scale up to 20, but then I wouldn't have had the 10 to get the 5. And you wanted me to do the strategy 5 is half a 10. So since I know 10 18s is 180, I now know 5 18s is half of that 180. Since 5 is half a 10, then 5 18s would be half of 180, which is 90. Now I have 20 18s being 360, 5 18s being 90. And so I can add the 20 and the 5 together to get 25, and the 360 and the 90 together to get 450. And I totally just thought about angles when I did that. 360 and 90 as angles to get the 450. Anyway, so 5 is half a 10 is using this relationship that's so cool in our base 10 number system that I can find 5 times anything by finding 10 times that thing and then cutting it in half. And you might be like, whoa, why would you want to go to that work? Well, it's because 10 times things are so easy to find, right? In our base 10 number system, multiplying times 10 is so easy because there's that 0 thing, and we can talk more about that. But I can just use it. I can use the idea that I can do the scale change where if scaling by 10, I can kind of shift things in the place value, or I can think about that and then just cut it in half to get times 5. Bam! I've got that times 5, and I can use that times 5 however I want to. Cool. In this case, I just added it back to the 20, and then I've got
smart partial products. Yeah.
Cool. All right. So what do we have so far? We've done partial products, which isn't one of our 5. Then we did smart partial products. We did over and under. We just did 5 as half of 10. Before we go on, Kim, if you don't mind, I want to just note that all 4 of the strategies was talked about, kind of the baseline partial products, and then the other 3 that are 3 of our favorite 5. All of those are based on the distributive property of multiplication. So the distributive property of multiplication says that I can sort of distribute, like, which means I can find these chunks of area, and then I can kind of chunk them and add them together. So that's the distributive property. Because the next 2 are going to be based on the associative.
This is one of my favorites, right? So, and this one's
all right, Kim.
This one,
double and half for us.
The name, right? We get stuck on the name here because
for this problem especially,
I think you've made some offers before that if we have a better name that encompasses all that this strategy entails, that we definitely want to hear it. But for this problem, I would absolutely think about double half, because I know that if I have, and I actually think about this one as 18 times 25. So is that legal? Can I
use the commutative property?
Can I think 1825? Sure. Okay. So instead of 1825s, I want to create an equivalent problem that is 9 times 50. So instead of 1825s, I need, if I want half as many of them, then I need, I always say this wrong.
As much
I need twice as much in a group. I need half as many that's twice as big.
Yeah.
So instead of 1820 times 25, I want 9 times 50, because I know that that's 450.
9 times 50. You can think about that.
Mm-hmm. Yeah, I do, because I know 9 times 5.
9 times 5 is 45. Scale that up by 10. That's 450.
Yeah. Yep.
Or we could keep going. If you're thinking about 950s, you could say,
I could think about
keep going.
4.5 times 100.
Place value shift, and that's also 450. 4.5 times 100. That's kind of fun.
Yeah.
I like it. So doubling and halving, we could totally think about how Kim just said. If I'm going to have half as many groups, the groups have to be twice as big. I could think about it the other direction. If I'm going to have, so if I was thinking about 25 18s, but I could say I want 50. I want twice as many groups. But if I want to keep the same amount, then I got to have them be half as big. So instead of finding 25 18s, I'm going to find 50 9s. This is twice as many groups that are half as big, 59s. It's just another way of kind of thinking about that. But we could also look at an area model for doubling and halving. If I looked at an 18 by 25 area model, and I cut that 18 in half, so now I have a rectangle that's a 9 by 25, and another 9 by 25 sort of piece, and I kind of shift that piece over next to it. So now I have a 9 by 25 next to a 9 by 25. That turns into a 9 by 50. And that 9 by 50 has the same area that I had before I cut it up. And so since I have the same area, then the products are equivalent. So cool. And this might spark in you a very, very similar to some strategies that we did in addition and in subtraction, where by using this strategy, we've created an equivalent problem that's easier to solve. So in addition, when we do a little give and take, why do we give and take? Because we create an addition problem that's easier to solve. In subtraction, we shift the distance. We think about the subtraction problem as distance or difference, and we shift that distance or difference on the number line, and we create a subtraction problem that's easier to solve. With doubling and halving for multiplication, we move area around a little bit, and we create a rectangle with the same area, or in other words, a multiplication problem that's easier to solve. We create an equivalent multiplication problem that's a little bit easier to solve. Those are cool strategies when it's all about creating an equivalent problem that's easier to solve. We like those strategies. Very nice.
Yeah.
I'm looking at the time. I think I have just a little bit of time. I'd like to describe a little bit how that's based on the associative property, if I may.
Sure.
So when I'm thinking about 25 times 18, I could also think about that as 25 times 2 times 9. And right now, when I think about 25 times 18, the 2 times 9 is associated. So I'm thinking about it, 2 times 9 is 18. But if I reassociate that 2 and instead think about 25 times 2 and then kind of leave that 9 hanging out there, 25 times 2 times 9, I'm associating the 25 times 2 and leaving the 9 out there. That 25 times 2 is 50, and I still have that 9. And then I turn it into that 50 times 9. Bam, I've reassociated that 2. Instead of having it sort of in that 18, I'm pulling it out and I'm associating it with the 25. And that's how I'm using the associative property. Yep. So cool. So stinking cool. All right. Last strategy. Before we actually do the last strategy, I was just going to say, we have these 4 major strategies. And when I got really serious about, like if we never teach kids an algorithm, if I never use an algorithm, and really I was thinking about my own personal kids, because my own personal kids were the grand experiment. Like, what if they never ever see a traditional algorithm? Will they be able to solve any problem that's reasonable to solve without a calculator with the strategy that we've developed? And I decided not quite. With the 4 that we've just talked about. Golly, can I go over them? Smart partial products.
Smart partial products.
Yeah, help me.
5 is half of 10. Double half.
With those 4, would I be able to solve any of them? Is there another strategy that we need so that we can really solve any problem that's reasonable to solve without a calculator? And I decided to add this one last one in, and I call it using quarters. Using quarters. Kim, am I doing this one, or you want to do this one?
Yep.
Okay. So 25 times 18, I'm going to think about, I could think about it in 2 ways, but I'm going to think about it as a fourth of 18. I'm going to think of 25 as like 25%, 25 out of 100. And so if I think about a fourth of 18, let's see, a half of 18 is 9. And so a fourth of 18 would be half of 9 is 4.5. But that's like thinking about 0.25 or 25 hundredths times 18, right? A fourth of 18 is like 0.25 times 18 is 4.5. But I want 25 times 18. I want 100 times that. Now, I don't want just 0.25 times 18 or 25 hundredths of 18 or a fourth of 18. I want 25, not 25 hundredths. So I've got to scale that 4.5 times 100. 25 times 100, or 4.5 times 100 is 450. Now, you might be like, whoa, why did you do that crazy work with fractions? Well, it becomes really nice if the problem was actually like 75 times 18. Then I can say to myself, well, if 1/4 of 18 is like 4.5, then can I think about 3 of those 1/4s? Or I can think about, if 1/4 of 18 is 4.5, then 25 times 18 is 450. Then I can think about 3 of them to get 75 times 18. So I can sort of think about 3 of those. And so how are you thinking about 3 4.5s or 3 450s? I can think about 900, and then another 450 is what, 1350?
1350.
So 75 times 18 now becomes 1350. And now I can think about 76 18s by just adding one more, a little over under. I just tack one more on there. I can just tack one more 18 on there. Is that 1368? I mean, bam! Like, I'm solving all sorts of crazy problems based on sort of this fractional relationship. And not only am I doing multiplication, but I'm also kind of practicing this idea of fractions, a fraction of a number, and I'm using a fraction as an operator, which is one of those meanings of fractions is so important, the fraction as an operator. So lots of relationships kind of come to play, and it can become the brilliant work that we do in sort of 5th and 6th grade, as we want students to be grappling with all of those ideas. And you might be like, Pam, why would I ever do that? I could just do these steps. I'm like, because remember, our goal is to build multiplicative reasoners. It's to build multiplicative reasoning in students. And this is a brilliant way to do it, to have them play around with these relationships.
Okay, do we have time for one more bonus strategy?
Yes, as long as we do it quickly. Because
okay.
I don't want, we want the episodes to stay manageable, right?
Yeah.
All right, cool.
So one bonus strategy for, give me a grade, give me an age.
I think it's sort of a middle school strategy. I think it's when we want kids really, like we just said, building multiplicative reasoning. And so we've kind of got kids kind of multiplying, but now we want to really get multiplicative reasoning.
Yeah.
And we call it
Flexible factoring.
Flexible factoring. Yeah, it's a...
All right, so I'm going to let you go. Go quick. 25 times 18.
Okay, so I would want to factor 25 into 5 times 5 and factor 18 into 2 times 9. And then I want to be flexible. Now that I have 5 times 5 times 2 times 9, I'm going to pull a 5 and a 2 together to create a 10. Because 5 times 2 is 10. What am I left with? I still have a 5 times 9. 5 times 9 is 45. And so I have 10 times 45 is 450. Bam!
Nice.
So flexible factoring is kind of an advanced strategy. It's not one of our 5 main ones, but we do want middle school teachers to develop it after, where you factor the factors in the problem and then rearrange the factors using the associative property and put them together in clever ways to create tens or create other numbers that are easy to multiply by. And then bam, you end up with another equivalent problem that's easier to solve. So that's also one of those really cool strategies. It's all about creating an equivalent problem that's easier to solve.
Excellent. Okay, if you haven't yet gotten yourself this fabulous download,
yo, what are you waiting for? Come on,
seriously,
download the guide.
So much help. All right, so it's got multiple strategies for each of the operations. You're going to find that download at mathisfigureoutable.com/big.
Because it's big.
Get it today.
Yeah, it is a big download. All right, mathisfigureoutable.com/big. Download that guide, because if you want to learn more mathematics and refine your math teaching so that you and students are mathematizing more and more, then join the Math is Figureoutable movement and help us spread the word that math is figureoutable. Thank you for listening and making math more figureoutable.
To learn even more, make sure you register for our free challenge at mathisfigureoutable.com/challenge. You are not going to want to miss the evenings of May 15th through 17th, starting at 7 p.m. Central.
Math teaching, go register now. That's mathisfigureoutable.com/challenge. Join us to make math more and more figureoutable. And if you can't join live, register and we'll send you access to the recordings. We'll see you there.